In the previous video, we discussed the product rule and addition rule of counting principle, and in this video we will be working out some problems using those principles. For those who are not sure what counting principles are, I suggest watching the previous video before continuing with this one. The first question is, in how many ways can we design a flag with 4 colors from the given 6 colors? So we have a flag with 4 stripes and we need to choose different colors for these stripes from the 6 given colors. While solving any counting problem, the first step is to name the things involved in the question. Since there are 6 available colors, let us name them as PG, VR, YB. The next step is to form examples by actually performing whatever is being asked in the question, that is selecting colors for the stripes. We can design the flag as red, green, yellow, blue, or we can interchange green and blue to form a new design, or we can replace red and yellow with violet and pink, and so on. Forming such examples help us to clearly describe the work and identify the parts involved in completing the work. In this case, work is to design the flag. And to complete this work, we need to select colors for the 4 stripes. By coloring any one stripe, we are doing a part of the work, precisely 1/4, that is 25% of the work. Coloring one more stripe will complete 2/4 of the work, that is half or 50%. Third stripe colored and 3/4, that is 75% work is done. Fourth stripe and 100% work done. So the parts of this work are to select colors for the individual stripes. Since there are 6 available colors, so the first part can be done in 6 ways. As the stripes have to be of different colors, so excluding the first color, a second color can be selected in 5 ways. Also, we cannot use this second color again, so for the third stripe, we have 4 choices. And for the last stripe, we have 3 choices. Since all the parts have to be done to complete the work, so by product rule of counting principle, we have the total number of ways of coloring this flag as the product of these choices. So it is as simple as that. Describe the work, identify the parts of the work, and then apply the principle. Let us go through a similar problem. So we have 3 colors, let them be red, green and blue. And we need to color these 4 triangles such that no 2 adjacent triangles have same colors. Adjacent triangles are those triangles which have a side in common, such as these 2 or these 2. Go ahead and give this question a try, pause the video and work out a solution. Okay. We have 4 triangles and only 3 colors, so obviously we cannot have a different color for every triangle. We have to repeat color, but we need 2 adjacent triangles to be of different colors. Suppose we color this triangle as red, this triangle as green, and then this triangle as blue. Then we will have no way to color this center triangle as it is adjacent to all 3 triangles and so cannot have either of the 3 colors. To avoid that kind of deadlock, we should not switch randomly from triangle to triangle, coloring them. Instead, after starting with any triangle, we should go to a triangle that is adjacent to the previous one. So if we color this triangle as red, then the next triangle should be this adjacent triangle, which has to be of different color. Let it be green. Now we can move on to either of these triangles as both of them are adjacent to the previous one, they cannot be green. We may color them both red or both blue or one blue, one red. So the work here is to color the triangles and has 4 parts, each consisting of coloring one triangle. Suppose we start with this top triangle, then we have 3 color choices for it. For the sake of discussion, let it be blue. Next triangle would be this adjacent one, which cannot be blue, so we have 2 choices for it, red or green. Let it be red. Now the remaining two triangles are both adjacent to the center triangle, so they can't be red, thus have two choices each. So this triangle can be colored in two ways, green or blue, and this triangle can also be colored in two ways, except red color. By counting principle, the total number of ways equals 24. Try doing the same problem starting with a different triangle. The next problem is, in how many ways can we put on 4 rings on 4 fingers? So we have 4 rings, let them be A, B, C, D, and 4 fingers, 1, 2, 3, 4. We can wear any ring independently on any of the 4 fingers. We can even have multiple rings on a single finger, assuming that the fingers are long enough to accommodate all 4 rings. Pause the video and give this problem a try. Okay. The work here is to put on all 4 rings, and the parts of this work are making choices for each ring. We can start with any ring, and it doesn't matter which ring we put on first and which we put on next. What matters is where we place those rings on 4 fingers. For simplicity, let us start with ring A, then B, then C, and then D. For first ring, we have 4 choices. We can put it on any one of the 4 fingers. Suppose we place first ring on finger 2. Then for the second ring, we have, let us count, 1, 2, 3, 4, and 5 choices. Of these 5 choices, suppose we place second ring on finger 1. Then for the third ring, we have 1, 2, 3, 4, 5, and 6 choices. Of these 6 possible placements, suppose we place third ring on finger 2. Then for the fourth ring, we have 1, 2, 3, 4, 5, 6, and 7 choices. By product rule of counting principle, the total number of ways is 840. So there are 840 different ways in which we can put on 4 rings on 4 fingers. Try doing this problem yourself, making placement choices for rings in your own way. Next question is, how many unsuccessful attempts can be made to open a number combination lock? This lock has 3 rings with 10 digits on them, which can be rotated to form a 3-digit code. Incorrect code will not open the lock and attempt will be unsuccessful. So what is the total number of unsuccessful attempts that one can make? Pause the video and give this problem a try. Okay. To make an attempt, we need to form a 3-digit code. This requires guessing first, second, and third digit of the code. First ring has 10 digits on it from 0 to 9, and it can be rotated and set to show any one of the 10 digits in 10 ways. As the digits in a code may repeat, so the second digit of the code can also be selected in 10 ways. Similarly, third digit can also be selected in 10 ways. So by counting principle, the total number of 3-digit codes that can be formed is 1000. Of these total 1000 combinations, there is only one which can open the lock and constitutes a successful attempt. So total number of unsuccessful attempts is 1000 minus 1, 999. The next problem is, in how many ways can we distribute 3 prizes among 5 students? Let the prizes be X, Y, Z and the students be from S1 to S5. The work here is to distribute these 3 prizes among these 5 students. One way of doing it is giving prize X to S2, Y to S4 and Z to S5. Or by giving prize X to S1 and both Y and Z to S3. Or we can give all 3 prizes to S1. So we are free to give any number of prizes to any student, and so for every prize we have 5 choices. To complete the given work, we need to distribute all 3 prizes, that is prize X and prize Y and price z. So by product rule of counting principle, we have total number of ways as 125. What if we add a condition that no student receives more than one prize? What will be the number of ways then? Pause the video and try to find the answer. Okay. Suppose we start with prize x and we have 5 students in front of us. So this prize can be given in 5 ways. For this example, let us give it to S2. Now let us distribute prize y. We can't give this prize to S2 as he has already received a prize and no student can receive more than one prize. So for prize y, we have 4 choices. For this example, let us give it to S5. Now for the last prize z, we have 3 choices, excluding the 2 students who have already received a prize. So total number of ways is 5 into 4 into 3, 60. Let us change the question again. And the condition this time is no student gets all 3 prizes. So a student may receive no prize, or 1 prize, or 2 prizes, but not all 3 prizes. Try this question yourself and then you can watch the solution. Okay. For the time being, let us ignore the given condition that no one receives all 3 prizes and distribute freely without any restriction, giving any number of prizes to anyone we want. So we can give prize x in 5 ways to any one of the 5 students. Also prize y can be given in 5 ways, not worrying about any condition as to who receives how many. Similarly, prize z can be given in 5 ways. So total number of different ways of distribution without any restriction is 125. Some examples of these 125 ways are as follows. In these examples, we can see that there are all sorts of distribution with students receiving from no prize to all 3 prizes. Let us focus on those distributions where one student gets all the prizes. Like in example number 3, where S1 receives all 3 prizes. Or in example 6, where S2 receives all 3 prizes. Similarly, there will be 3 more distributions in which student S3, S4 and S5 will receive all 3 prizes. So number of ways in which one student gets all the prizes is 5. And excluding these 5 ways from the total 125 ways of distribution, we have 120 ways in which no student gets all the prizes. The next problem is, if a table has 4 chairs on one side and 3 on the other, then in how many ways can 7 persons sit on them if 2 particular persons wish to sit on a same side? So we have this table with 4 chairs on one side and 3 on the other. Let us call these 2 sides as side A and side B. Also let persons be P1, P2, P3, P4, P5, X and Y, where the persons from P1 to P5 have no condition and they can sit anywhere, while these two, X and Y, want to sit on a same side. Note that they may or may not sit side by side next to each other. That is, suppose if X sits on this chair, then Y can sit anywhere on this side. Pause the video if you want to try this question yourself first. Okay. Since X and Y have to be on the same side, so we can classify the sitting arrangements in 2 types. Type 1, in which X and Y are sitting on side A. Type 2, in which X and Y are sitting on side B. The work here is to place the 7 persons on 7 chairs, and we must start by placing X and Y first, as they have a condition, and then we can place rest of the 5 persons. In type 1, X can take any seat on side A in 4 ways. After X taking up any chair, Y can then take any one of the remaining seats on the same side in 3 ways. After y occupying any seat, we can arrange p1 to p5 on any of the remaining seats on any side. So p1 has 5 choices. After p1 sits anywhere, p2 will have 4 seats to choose from. And similarly, p3, p4 and p5 will have 3, 2 and 1 ways to sit. So total number of type 1 arrangements is 1440. For type 2 arrangements, x and y both have to be on side B, so x can take a seat in 3 ways and then y can sit in 2 ways. After y sits anywhere on side B, the remaining 5 persons, just like in the previous type, can sit in 5, 4, 3, 2 and 1 ways. So total type 2 arrangements is 720. Now the sitting arrangements can either be of type 1 or type 2. So by addition rule of counting principle, we have the total arrangements as 1440 plus 720, that is 2160. That is all for this video. Here are some questions for practice. Note them down or take a screenshot of the questions and try solving them. In the next video, we will be discussing arrangement of distinct things and restricted permutations. In case of any doubt, either comment below or mail me at this address.